Okay, good. So we're recording. Welcome, everybody. We've got some guests in the room. Thanks for coming. Today, we're going to do something just a little bit different, but strongly related to the class. So for those of you who are not in the class, this is Connected Embedded Systems. As part of what we do here, we actually build stuff. And it turns out that this year we're really blessed to have Cody in the class. Cody knows a lot about 3D printing. So he's going to take us through the basics, and by the end of the class, you'll have a pretty good idea of what you need to do to actually do a 3D print. And he's going to actually do a live demo for us. So this should be really very satisfying. So Cody, take it away.
Thank you, Bob. So I have a 3D part we're going to print in this little lecture. It's going to be this part right here. And I specifically designed this to print sort of just in time. So I'm going to go ahead and start that off before we get going here. So the way this works is, we'll talk about this, but you'll have a design. You'll save it to an SD card. You'll put that in the printer. Go to the main menu. Print, reads the card. There's the part file. It's going to tell you how long it's going to take, and you're off to the races. So that part is easy. Hello, come on in, guys. So what that's going to do right now is, I've already had it preheated, but it's going to heat the nozzle up, and it's going to start printing in a second here. So welcome to Bits to Blobs, Adventures in Rapid Prototyping, 3D Printing, and Computer-Aided Design. My goal for this little lecture is that hopefully everyone here goes from a point where they can have an idea for a part they'd like to make and be able to take that completely through to reality, to be able to print a physical part using some of the machines we have available here at this campus. So my background, this is funny. I had a TA ask me in FSC to introduce yourself to the team, and we had done this a few times. And I said, "Hi, I'm Cody. I like to build robots and occasionally blow things up." And without missing a beat, he said, "Oh, that must be why you and Bob are getting along so well together." Yeah. So I come from a world of 3D animation. That's kind of what I was doing in high school. A lot of work with 3D Studio Max, and that that and competitive robotics kind of led me to many avenues. And there's sort of this, hey, Brad, sort of this spectrum of mechanical engineering, electrical engineering, computer science, stuff like that I've accumulated over the years. The significant parts of this is that to our lecture today is the fact that I've worked with many different CAD packages, and I've done many years of 3D printing. So you wouldn't download a car. Maybe 10 years ago or so, if you went to a movie theater in America, you'd see these little adverbs that tried to link physical crimes like stealing a car to computer piracy, sort of virtual crimes. And so, a couple of years later, big 3D printers came around, and they started to demo parts like rims of tires and things like this. And so the internet, being the internet, put together a little meme and said, "Yeah, no, we would download a car if we could." And then, of course, a couple of years after that, we start to see 3D printed cars, or at least partially 3D printed cars, hit the market, or be in the development phase. And so it's an interesting evolving industry where the concept of being able to make something sort of from a digital file, just push button go, is kind of rapidly becoming a reality. And this sort of takes me back to sort of my sci-fi base. Who here is familiar with Star Trek? Oh, come on, I know more of you. Yeah, I see some hands slowly come up. Yeah, so in Star Trek, they have this wonderful suite of ideas that were incredibly just out there science fiction, the stuff of dreams, right, back in the day. And one of the big plot sort of ideas that they kept coming back to was this machine called the Replicator that you could walk up to and just talk to, and you could basically ask it for stuff, make me a cup of coffee. Cup of coffee shows up, And it was interesting because the show defined really good rules around the Replicator. The ship's computer had a database of patterns. And if it didn't have the pattern for what you were asking for, it could only make what you wanted if you were able to sufficiently explain to it what you wanted, and it could derive that from one of the patterns it did have, which I thought was really, really awesome, interesting. And there's probably a million different directions I could take with that. But this is sort of the master vision for 3D printing, the idea that we could just have stuff pretty much instantly for no cost and to a certain customizable degree. And this is a sort of more grounded version of this. Ideally, we would love to be able to take raw materials and turn it into arbitrarily complicated things. It would be great if we could have a building, black box, right, with dump trucks of aluminum powder coming in one direction and $180 million Falcon Heavies coming out the other side. In the actual world, things are a little different. Right now, for about $2,000, you can get a commodity printer like that one right there. I paid $1,600 for mine. That can print thermoplastics, this stuff. We'll talk about this stuff in a second here. But these are basically plastics that at room temperature are stable in a solid state, but can relatively easily be brought to a liquid state and then back again. That's what a thermoplastic is. This is PLA. We're printing in PLA today. But there are other materials that we can print in. That printer can do ABS, PET. I don't think that machine can do nylon, but the other one probably can, I'm going to guess. So we have limits in what we can print. We can't just print cake batter or metal or carbon fiber or whatever, right? We have to know that our machines are already going to have material limits. And then the number of materials we can print with consecutively in a print is also limited. That machine can do one. Bob's got a machine that can do two. There are FDM printers. We'll talk about what that means in a second. That can do up to 4, kind of where it tends to top out. And there are other printing methods that can start to get into that multi-material land, and we'll talk about that in the end. We have lots of limitations. Printing is really slow. It's going to take the specifically designed part, still going to take half an hour to print. Hopefully, is that doing all right? I think I'm not for me. Low volume, low yield, so you're going to expect to lose some of these parts if you try to make any level of production. Okay, good. The filaments cost more than we'd like, although they are pretty cheap, and a myriad of problems. And these are all dimensions that we could address from an engineering standpoint. You could build a printer that's fast, probably going to cost a lot of. You're almost certainly going to, by pulling one constraint this way, you're probably going to bring others down, quality or something like that. That's just sort of the real world. The rapid prototyping. We are going to talk today about 3 sort of master steps. In the first step, we're going to talk about how to take an idea and turn it into a 3D model. We're going to use a CAD tool to do that. CAD stands for computer-aided design. It just means anything where you're working in conjunction with a computer to accomplish a goal. The second step is the one that I think most people miss in their mental picture when they think of how do you take a part to a print. It's slicing. So in this step, we're going to take our 3D model and we're going to turn it into a set of instructions. So by the end of that step, that printer can execute a really simple set of instructions that basically say, heat up, go here, start putting out filament, move over there, things that it can understand. And then hopefully, if we do all of that intelligently, we end up with a finished part like this. While I'm doing this, I have a box of 3D printed parts. If you could take one and pass it around, is my thought here. So everyone has a part to sort of play with in their hand. We have a robot that I printed in my senior year of my undergraduate. So you guys are welcome to pass that around as well and check it out. Props are good. Okay. FDM 3D printing is a specific way of 3D printing. We're going to talk about how that works on this slide. It stands for fused deposition modeling. It works like a hot glue gun, basically. If you've ever played with a hot glue gun, you've got a trigger, a stick of glue, and a hot part in the end. And basically, the trigger just pushes the stick of glue forward. Out a little nozzle comes the hot glue. It's exactly what's going on here. You've got a set of filament, this stuff. You pinch it through 2 counter-rotating gears. And in doing that, you get a rack and pinion effect where the filament now moves in a linear fashion from your rotational movement. We do this with stepper motors that we can precisely control. We guide that filament into a hot section of the printer called the hot end. The thermal picture here is a little bit simplified. There's actually a lot of complexity in exactly how you do that. But essentially, we heat it up to just over its melting point, transitioning it from a solid to a liquid. Comes out of a very precisely machined nozzle. The one on this machine is 0.4 millimeters. That number will be important a little bit here. And we use a gantry system not shown here to position this whole process so that it happens at exactly the right space and time and at this right velocity as well. And if we do that right, we can create parts, essentially. Now, this slide, it's here because it's interesting to me. It's here because of this class. It's here because of a lot of things. I had a project I was working on where I was trying to do some modifications to my printer, and I really wanted to study, like, how does this from a system standpoint work? And I was really amazed to find that the CPU in that printer is the same CPU in an Arduino Mega. It's just an Arduino, basically. You can see here this pattern is replicated 5 times. You can kind of see it. Those are stepper drivers. This printer was designed with 2 extruders in mind, so there's an extra one not used. But right now, there's one controlling the X, the Y, the Z, and then there's one controlling the extruder. A couple of temperature output dealios, a 24-volt relay. Simple stuff. There's nothing crazy complicated. I can read the schematics, because I'm sure most of the people in this room could too. So that sort of is our basics on the printer. We're going to turn over to Fusion for a second here. And if we look at our part, this is what we'll end up with. This is a 3D CAD model of the part. So we can move that around here and do all kinds of fun stuff with it. We're going to make this real quick as a demo. And in doing so, we're going to learn how to think in 3 dimensions in terms of part design. We're going to learn a little bit about CAD tools and a lot of things like that. So I just wanted to sort of say that the exact steps I'm about to go through are not the important part here. It's the process. I want you to think about how we went from nothing to something, not what hotkeys I pressed and things like that. So in Fusion, we very often start things off with a sketch. So I hit the sketch button. I pick the plane that I want to sketch on. And for this part, we're going to start with a rectangle. So R for rectangle. And this part was 50 millimeters by, oops, I screwed that up. 50 by 70. So we have a rectangle. Move that in 3-dimensional space. I hit E for extrude. Our part's going to be 7 millimeters tall. So now we have a block. We would like the block to be rounded because we have these nice rounded corners, as you can see here. So there's a tool called the fillet tool, F for that. And then you can select these edges, which are a little bit hard to grab onto. And then if I hit 10 for the size, there we've got rounded corners. So this isn't that complicated. If I make another sketch on the top and I project the existing surfaces, which also isn't that bad. Actually, I think I can get the whole thing. Yeah, there we go. Hopefully that works. And then there is a inset tool that I have to find really quickly here. Where is that? Offset, yeah, it is. Yeah, down. There it is. Oh, okay, yeah. If I grab that, -1. This dimension is kind of interesting. It's going to be not 0.48 times 2. I'll use a formula to do that, and I needed to make that negative, so I goofed. But that's okay, because I can click on it, do that. Oops, no, I can't. I lied. O for offset, -48 times 2. That 4.8 is actually the width of an extrusion. We'll see that later. I said we had a 0.4 millimeter nozzle. The reason it's 4.8, we'll talk about. But what I basically just said is I'd like those walls to be two unit thicknesses wide. So you can think of the printer as kind of sort of a voxel printer, although it's not quite accurate. And if you know how it prints in the design stage, you can actually sort of use that and abuse that to your liking. So that's kind of interesting. We'll do an extrude. We will do this to a specific plane, the bottom plane. And if I were to do this right now as a cut, we'd sort of cut all the way through the part. I don't want to cut all the way through the part. I want to stop slightly before that. So I'll do that. Hopefully. Oops. See if that works. Okay, this is not being happy with me. 1 second. Rude. Distance, we'll just do 7 minus as a cut. And I need to hold on. -7. There we go. Sorry about that. Okay, so you can see what we're doing. We cut into the part. And finally, we have this little side cavity here, if you can see that. So I'll do a sketch on the side wall. And then there's this interesting little tool called the, where did it go? Where's my slot tool? Slot, there we go. Center to center slot. I can specify a slot, and then I'll dimension this out. So in CAD, if you, in sketch mode, blue lines mean they're unconstrained. That means you haven't sufficiently pinned them down. And black lines mean that they are constrained. So I have to sort of rigidly define every single potential variable here. Like right now, I can make this thing move or be wider. So that's kind of undesired. So I'll do a midpoint constraint on, actually I need to do a point before I do that. Let's see. First I'll dimension this out to B. 5, then hopefully we can do a midpoint. There we go. Excellent. So now that that's defined, get out of there, extrude this piece all the way as a cut. And there we go. And then finally, I'll fillet those little edges we created just because I don't like to leave sharp edges in parts if I can avoid it. That's just a human factor thing. I don't want to, this isn't a particular sharp material, but let's say this is aluminum, that would be a sharp edge and people can get cut on that. So we'll do 3.5 here as well. And then one last thing that I did on this part is I did a little tiny inner and outer fillet of 0.6, 1.2, and that is our part. And if I wanted to be fancy, I could go in here to materials and I could give it a color. That's fine. It's not going to affect the, not working, the plastic. Nope, that's not what I want. Paint, plastic, page. Yes, I could give that a color. It's not going to affect the print color, but it's nice for the CAD. Now, Fusion can do a lot more than this. It does assemblies and joints and static and analysis, dynamic analysis, and rendering and all kinds of stuff. But hopefully, that gave everyone an idea of what that process is like. Any questions regarding the CAD? How we got there? Yeah, please.
Like for the small fillets.
That would actually print itself. Yeah. So the layer size of a print and the width of an extrusion you can tweak, but for this printer, 0.15 millimeter layer height is what you can expect to get reasonably, and with that nozzle you can expect the 0.48. So you can think of like a 0.48 by 0.48 by 0.15 or 2 box, and that's sort of kind of at the level the printer's doing. I say sort of kind of because the XY axis can actually move dynamically. So you can give that, you can paint almost like vector in that dimension, but it's still going to get sliced into layers, and we'll see that in the slicing step, I think. That's a great question. Any other questions?
Quick question.
Yes.
Now, The software comes with it.
This one does not. That's a great question, though. Fusion 360 is free for anyone with a .edu account and any company with less than 100,000 in profits for the year, essentially. So Autodesk makes this tool, and there are many alternatives. There are free alternatives out there that do very similar things. That you've worked with SketchUp, right, Bob? And so one of the things that's nice about 3D printing is you can actually import a lot of different geometry and a lot of different formats from a lot of different programs. This is just the one that I like to use. I do find that Fusion is very capable, and I'll go to bat for it, so to speak, but it's not by any stretch of the imagination required or anything like that. We actually are going to use a slicer that is also not what comes with the machine, and then I'll explain that in a second here. I'm going to skip that video. Oh, sorry.
So for any structure that you're designing in this software, would you recommend doing a static dynamic analysis, like the stress analysis?
I mean, you could, because like this part's bendy, and if I didn't want a bendy part, you could look at that and potentially put the material properties in there. Now, it's not going to be able to model every little intricacy of 3D printed part because you tend to find that on layer boundaries you have less strength than in the layer, and we'll talk about that too. But yeah, if you're interested in that, I mean, there's a whole world of different filaments and materials that try to get material properties. We had a 3D printer at Inworks from CU Denver that could print Kevlar into the part and carbon fiber and whatnot. So if you wanted to do like really thermally intense or sort of stress or strain loads, you could potentially design that into your part and simulate that. Anyone else? Yes. How much error?
Yeah, because it's your vibes and
Right. Okay. Clearances. Gotcha. Yeah. So in a not 3D printed world, clearances are a big subject. And so machinists who work with metal and subtractive processes will talk clearances all day long. For what they call a loose fit, you're usually looking at 9,000ths of separation, maybe 11-ish, something along those lines. But so you'd model 9,000 the distance. You could convert that to millimeters. It's about 0.2 millimeters, 0.002, I think, millimeters. But the point is that with 3D printing, and this is on one of my slides, you're going to want to sort of take what you would normally think of and multiply that by some factor to deal with the error. And it's going to depend on what printing process you use. Do be aware that this material will rub away. So if you have like a metal part that you want to interface, if you can physically get it in there, you can probably round out whatever shaft or hole or things like that. I've done that before with screws, for example. I've just used the screw as a tap basically, and it works. So if you do it right, trial and error though is a good one too. Like you can print relatively inexpensively, and you can sort of figure out where that boundary is, and that's part of the fun part of this, I think. Well, anyone else? We have questions at the end. This part costs a couple cents to make, basically. Okay, so slicing is the process we talked about before, where we're going to take the model that we just made and we're going to turn it into the actual code for the printer. Now, these printers tend to run G code, which is a ANSI, ASCII kind of text file based code that comes from the machining world. Hello, hey. And it's really simple. It's literally like go from here to here at this speed kind of instructions. And machines will be tuned and calibrated and set up to do that. And so the machine's responsibility is to deliver on that line of G code, to say, okay, I will go from here to here at the speed that you specified, or I will turn the heater on to that amount, of things like that. Our job right now is to take that 3D model and figure out how to make those instructions from that part. So I use a slicer called Simplify 3D. This is Simplify 3D. And I'm actually just going to deviate from the slides here. If you're in Fusion and you've set it up right, and setting it up right just means pointing it at the program, you can hit this Make button and you can hit 3D Print. And I've set it up to export to Fusion. So all I have to do is click on the part, hit OK. Export to Simplify. and it brings in the part. So it's on the little bed there. If you don't have that set up, you just file export the part as an STL file, usually stands for stencil file. It's just a file format. It will meshify the part at that point, so you will go from vector-based geometry to polygonal-based geometry, which is important to know and understand, especially if you're thinking of downloading STL parts from the internet and using them in your projects. You're going to find that trying to modify them can be kind of difficult. At this stage of the game, though, what we're interested in doing is telling the printer sort of how to lay out our parts. And this could be important because let's say, for example, that I already have 2 parts. No, I don't. Oh, that one's disabled. Okay, yeah, let's say I had 2 of these to print, or I had many of these to print. Exactly how you lay these out matters. So you could do multi-part printing if you want. You can print different parts with different parameters and procedures. For the time being, we're kind of only interested in the one. So the layout is important for that reason. Beyond that, you have this process dialog that's got essentially a ton of settings that you could get into. And I don't have time to get into these, unfortunately. But a lot of the tweaking that you can do and experimentation is kind of in this panel right here. And then once you're done and you're happy with that, you can hit the button in the bottom left, and the conversion to G-code just happened. So we actually already have instructions for the part. And if you look here, I could do this, right? If you look really closely here, you can see exactly what we're talking about. You can see each individual bead that the printer is going to make. You can see that wall thickness that we specified to be really precise. We got what we wanted. We can see the layer heights. And what's fun about this for me is you can actually tell Simplify 3D to give you a little bit of an animated preview of how that part is going to be built. And then if you're really interested in specifics, you can turn on different display modes and get a lot of information out of that. So this is showing feature types. So if you want to go back to that dialog and tweak something, you can kind of ping pong between that and here to get where you want. And at the upper left corner here, you can see, perfect, okay. So you can see an estimation of how long the print's going to take, how much it's going to cost, how much it'll weigh, how much filament it'll use, things like that, which can be very useful, especially if you are making a bunch of parts. So we're almost there. Get past that. If you want a 3D print, once you've got this where you want it, you hit the little SD card button, you export your file to the SD card, you stick it in the printer, you hit go. Now, if you're in the lab, check with somebody, Brad, whoever runs the printer, Bob, if it's his printer, make sure you can get time on the printer. Some parts can take a while. That robot that we passed around, the body part of it, it's a 35-hour print. It's going to tie up the machine for 35 hours. So, for longer prints, that you're going to care about that. Turn on the machine, the switch is on the back. You may need to change out filament. The roll that's on there may not have enough for what you want to do. It may not be the right material, may not be the right color, whatever. So if you need to do that, Google the Ultimaker 2 manual. They've got these really nice animated picture, exactly how to do it. There's a wizard that'll do most of the work for you on the printer too. Unload the material that's on there, load the material you want if you need to. Clean the bed. The bed gets glue and dirt and grime and stuff on there, so most of that stuff can be rinsed off with water. So you just take the glass out, go find a sink, put it back in, insert your SD card, preheat the printer, and then finally make sure that the first couple layers print correctly. That's where things usually go wrong, is if your part doesn't appear right or the extruder's not extruding or whatever, you're going to discover that in the first couple layers, typically speaking. I'm going to skip over this slide, but handling filament's important. You can see good filament versus bad, and we'll talk with Brad and see if we can get some procedures on that. And then finally, sort of my tips slide. I have a couple other of these that are on the longer slide deck, but do really pay attention to the first layer. I designed this part so the first layer had a lot of surface area with the bed, but it wasn't too thick and it wasn't too large, so that as the part goes from 210 degrees C down to 60 C, which is the temperature the bed stays heated at, what it wants to do is it wants to contract, right? It wants to, because it's cooling, it wants to contract. So you have forces that are kind of pulling inwards, and you have static forces that are trying to hold it to the bed. And if the inward force exceeds the ability of the bed to hold it down, the part just snaps off the bed, and your print's gone. You're done. Just try again. It happens all the time. Parts peel up in the corners and things like that. So you want to try to have like just the right amount of surface area with the bed. Too much, bad. Too little, also bad, because your part may get knocked over or just fall over. It happens. Orientation matters. This is I was talking to some PhD students just the other day, and they printed this part this way instead of this way. And the printer tried to print on nothing, and you get that mess. It doesn't work. Gravity's a thing. Yeah, so remember, gravity's a thing. This is less of a you don't have to worry about it kind of thing, but if you do have your own printer and you're at home, don't put it next to the heater or the air conditioner. The thermals that are going on in there are like fairly sensitive to outside forces. So, if it's cold and you got a window open, don't print next to the window. I mean, it gets tempting because sometimes these things smell when they print, especially ABS, but you want to try to take care of that. Be willing to experiment. Filament really is cheap. You're paying like a lot of money to be here. There's no way you could run through enough filament to make anyone angry, I don't think. I don't know, maybe Bob disagrees with that, but if a part fails, don't worry about it. Chuck it in the trash. Try again. It's not a big deal as long as you're not stealing the printer from somebody else who needs it for too long or whatever. And understand. This is what I was talking about, the tolerances, by the way. Understand that the printer does have really finite limits, but challenge yourself to push right up to those limits. I have wheels for this robot that are 2 layers thick and 1 shell out. So like I'm thinking at the level of exactly what can I do with that printer, and I'm right up to it in the design. So we do have a couple of videos of some really interesting developments in 3D printers, but I'd like to open the floor up at this point and ask you guys any questions and have a conversation, I think. Any questions about what we covered in slicing?
How many people have actually?
I guess I have to.
How many people have an idea of something that if you had the opportunity, you would rush right down and print something? How many of you want to actually try it? Oh, come on.
Oh. I do.
Be here on the line. Seriously. So I think we should, take some more questions, show the videos, and then maybe we could convince you to go back over that sleight of hand that you did when you did the design. At no point did his fingers ever leave his hand, but they move so fast.
Yeah, no problem.
Worth going over
so one of the
basic steps, but don't only finish the questions and roll the videos.
Yeah, one of the nice things Fusion can do is kind of animate what you did. It's cute. So you can kind of see, like it's really interesting when I do the robot. It's like the so we can we'll go back to that. It's fine. I'll play one of the videos. Yeah, that'll be great.
From a lab constraint, it looks like timing is the constraint, not the cost of the material.
Right.
It can be, and the cost of the printer is you got to absorb that over how many prints. So like my printer that got destroyed by the post office, unfortunately, did what you see in that box. You got to ask yourself, does that look like $1,600 or not? So, but hopefully you don't ship your printer with USPS like I did.
I mean, Blobs 3D printer is different from.
Blobs is the same process. It's an FDM printer, the same slicer, the same CAD would work. It's nicer built, it's bigger build volume, and it's got a second extruder, which means that you can do dissolvable supports or just 2 materials, which is quite nice, actually.
It's also enclosed.
Yes.
Plastics like ABS, right? Really need environmental temperature control much better than an open printer like this. Herman went nuts trying to print ABS with this, and he had cardboard boxes around the printer to keep it all snugly.
Did anyone take the orange wrench by chance? Yeah, that's a part that, sorry to interrupt, but that's a part that was printed not that part, but that was designed. No, I'm sorry, the orange wrench. There's a wrench in here.
NASA wrench.
Yeah, I think it's in there. Yeah. This is one of my favorite parts. This was designed by NASA, and they sent it up as a design, like a file, up to the International Space Station. They've got a nylon printer up there that does microgravity printing, which gravity doesn't apply for them. They're fancy. And this printer, this part actually latches. Like you can, yeah, is that cool or what? And so ABS is bendable, so is PETG. So like PLA will snap if you stress it too much, but this stuff will deform. So there's a little tiny arm that's just in there. It's like only a couple layers thick too. It's crazy. And I like wondered how long until this thing eventually goes. But this you can see all the thermal crap that happened at the bottom because I couldn't keep it hot enough for it to remain dimensionally stable. So that's a part that like only barely printed on an Ultimaker. So you can kind of get an idea of where those limits are.
Did that answer? Did you get your question answered?
No, I'm more concerned.
I'm
about,
sorry.
from a resource perspective, in terms of. So, if I wanted to use a particular printer, that's fine.
Yeah.
What would be the constraint? I mean, I couldn't use it. I couldn't design something that'll take 24 hours.
Sure you could.
Yeah, you could.
I mean, practically speaking, this printer, well, Brad probably is in a better position to answer the question, so why don't you answer the
It's
question?
underutilized is the word you're looking for.
Okay.
When there's a queue of people a week long, then we'll talk about problems, but until then, I don't think it's, when your prints go 24, 36 hours, pushing the boundaries of the machine as well.
Yes.
So,
That part there, the body part, I actually had the bed telling you about this shift about a little tiny bit that way, and you could see it in the part. And like you wouldn't think this thing clamped down could do that, but over the course of 35 hours of, it vibrates out of place. So, that happens.
let me answer one other question.
Sorry.
Filament is about $30 to $40 a kilogram.
Mhm.
One of those that the tool that he has full is a kilogram. A kilogram is a lot. How much did your robot body? What was that? Maybe.
Oh, that's the third of a roll about.
Okay.
Yeah.
So that
A couple dollars.
$15
Yeah, something.
of materials. Yeah, it's like.
Yeah, but don't tell the school. I had a budget sheet that was like $99.9 something cents. Yeah, that project. Yeah. Okay, I'm gonna play a video about a technology that's a different type of printing. It's really exciting. We had one of these printers at Inworks. It was a $250,000 printer, but it's super nice. Yes, this is from Shapeways. This is a powder process. So good catch on that. I meant to mention that. I was going to say there's one special part in there, and that's that.
PolyJet is a 3D printing method that makes beautiful, precise models in a huge variety of materials and colors. It works like an inkjet printer, but instead of jetting drops of ink, PolyJet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts, soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
So Stratos is a big player in the 3D printer industry. I actually worked with a project with CU where we were trying to, we had a couple blind students at the school, and they were in a biochem class, and they were having a real hard time braille printing pictures of the molecules in the books. So we experimented with different materials, different surface properties, different shapes, different weights and sizes to try to essentially recreate a periodic table via touch, which is like an interesting project because you think about the rows and the relations and how you might do that. This is a small video of a concrete robot arm. I think really changed the way we think about construction. You get they printed the concrete shell of that house, and then finally, there are many companies working on approaches to doing metal 3D printing, which is like, ooh, fancy.
At up to 100 times faster than laser-based systems, it's the first metal 3D printing solution for mass production. It works by combining 2 powder spreaders and 1 print unit into a single pass system to both spread metal powder and print. Unlike existing metal 3D printing, there is no wasted motion with single pass jetting. A single pass starts in the powder spreader, where a metering system deposits metal powder, and a compacting system forms a layer, as thin as a human hair. The print bar follows, jetting droplets of a binding agent. Millions are jetted per second, binding metal powder to form high-resolution layers. Anti-sintering agents are then deposited, making it possible for supports to fall off after sintering, saving hours of post-processing. Once the layer is dried, the process repeats itself. Single-pass jetting is bidirectional. We combined all the necessary steps for printing into a single pass, so that whenever there is movement, there is printing. This makes it possible to print parts in minutes instead of hours. Once printed, the brown parts are densified in a microwave-enhanced furnace. It combines conventional heating with microwaves to speed up sintering. A closed-loop thermal control system regulates temperatures in...
It's fancy, it's expensive, you get the idea. Metal 3D printing is on the horizon. So that's really interesting. Another sort of approach to this is from a CNC perspective, where they're taking these really interesting 5-axis CNC machines. These things cost more than your car. And they basically take a welding. Think of like the welding rod filament. It's really interesting. Aerospace that ever make vermillion of traction that hybrid of both add and remove as needed, because we can get more precision removal than we can get in printing. So ideally, it'd be all added, but right now, mix is proving to be pretty potent. So it's just really interesting. So I've seen Autodesk do some work on this with those KUKA arms, trying to 3D print in ways we never thought of reaching before. And you still be oversized. Care about how it's happening. With the possible. So like the blade. That's for a good example. Mostly smaller, and being used, and there's a lot of trade secrets and carbon composite work being put there as well. So there you go. I'm not going to play that video. So I am done, Bob. I think I'm done. Go back to questions if you want.
Questions?
Cody, I have one. What are the factors governing the speed of the printing?
That's a good question. So in S3D, you can set the XY travel. And if you set it too high, at some point you start asking the machine to do something it just can't do. So I believe I was printing at 16 or 1700 millimeters per minute or something like that. There's going to be a point where it's like it's fast and it's consistent, and that's where you're going to stop. And so, building machines that with gantries that have linear motion that can go faster, sure. At some point, your extruder becomes the limit how fast you can push the material through, especially when you're doing like really imprecise. Like there's this extruder called the E3D Volcano. It's like huge, and it can just print very inaccurate but large things quickly. And it turns out that keeping that thing sufficiently fed is a challenge. And that goes back to the concrete printer. You don't really care how precise it is. Your speed would be the dominating factor there. And that goes back to the constraints we talked about, where if you pull on one, you're going to lose others. So speed usually means accuracy trade-off. And of course, quality of printer matters. It's why Bob's printer is going to print faster than the Ultimaker, and et cetera, et cetera. And process too. How you print the part matters. So for FDM, honestly, FDM is not the leading edge anymore. It's why it's cheap, because the big 3D printers can sell proprietary stuff that we, for lots of money that we don't get. PolyJet, for example. Okay.
So what's a good starting point to learn more about the design process?
Great question. Yeah. So if you pick a tool, you can go look at what's out there. 123 CAD, SketchUp, 3ds Max. There's plenty of modeling tools. You're going to want to pick, if you're really serious about this, you're going to pick a vector-based approach. So like polygonal tools use polygons and triangles and stuff. You can print it, but you're going to get more precise results with the vector-based approaches. Find a tool you like. Go on YouTube. Find someone that does tutorials on it. If you want to learn Fusion, I highly recommend a guy's channel, New York CNC. There's a guy, if you're into machining and CAM stuff, Grimzone Eyes does a really, really good look at how they build their products, but that's not printing stuff. And then there's a couple guys out there who are just 3D printing is their thing. I get millions of subscribers of just 3D printing, and so you can kind of find those guys. I think Joel, the 3D printing nerd, is one of them, and they kind of review machines and go into the real details of this. But for just on the CAD side of things, honestly, networking is part of it. Having someone that can sort of sit down with you and go, okay, what do you want? If you brought me a sketch of a part, I'd sit down and work with you on how to make that part. But there are resources out there. Fusion has some help libraries and things like that. My recommendation is to do a project. Find something you want to make, go make it, and rinse and repeat. My last slide had, iteration is how we get better. I very much believe that. Did you have a question, Brad? Crazy?
I was going to say, if any of you want, when you get to the point that you've got your STL file or whatever like that, I'm happy to give you one-on-one training on how to make. Not hard, but there's a few minutes of, change the filaments to get it started out.
And like I said, there's really good guides online on how to do all that stuff. So
Ultimaker is very well supported.
I really like the Ultimaker community. I've been happy owning one, and till it died from the post office. Yeah, I'll bring it back. It's cool. All right. Anyone else? Going once?
So how much does it cost?
The printer?
First, I wanted a personal Ultimaker.
I got mine for $1,600 lightly used a few years ago.
Yours?
How much do we pay for it?
Bob's like, oh. Yeah, they paid sticker price.
So this is sort of that's a range for.
You can get cheaper printers. So if you want something to play around with, and then you want to come here and use a nice one once you've got what you want figured out, barrier to entry is probably $1,000, I would guess. On the low end. Yeah, those printers suck. There's a limited level of use, I think, that you want to be above a certain level and before, or you're just burning money, in my opinion. So I don't know.
Yeah.
Thinking of doing that?
No, my son was playing around with this stuff, and it was a $300 printer. It was crap.
Yeah, that was yep, basically.
Dad needs to dig into the wall.
Your Make Magazine runs a survey. You go to makezine.com, whatever the website is, and every year they do a review. Ultimaker's been and they have a whole spectrum. And yes, they start at a few $100, and those are the ones at the bottom. Then $3,000. Pretty much any of them that are $3,500.
Don't buy a MakerBot.
Don't buy a MakerBot. Buy Stratos.
Well, they were ruined before that, but yeah.
Stratos is great.
Yeah.
So the MakerBots are very much on the do not touch.
Stratos gets a bad rep because they're the people who like to patent every good idea around 3D printing and then make everyone wait 20 years before they can use it, basically. So Stratos gets a bad rep for doing that. All right, thank you guys so much. If you have any questions, bug me anytime.
Thanks. Bob, in your course,